It's a pleasure. It's a pleasure to be here and to start the second session of this seminar, online seminar. So I'm really happy to be here. And today I will talk about not a theoretical aspects of ISS or about abstract control system or this kind of thing, but I will more explain how ISS Lyapunov functional can be used in the output regression task for a specific PDE, which is the Korteweg-de Vries equation. And I will also explain how from a weak Lyapunov functional, so I will explain what I mean by weak Lyapunov functional, we can strictify this weak Lyapunov functional into having a strict Lyapunov functional, which is ISS with respect to some control or disturbance. So this work is a joint work with Ismaïla Balogoun, who is my PhD student and is finishing his PhD. So in 2 months, he will defend his PhD. And the joint work with Eduardo Serpa from Chile and Daniele Astolfi, who is a researcher located in Lyon. So here is the system that we will look at during this seminar. So this is a PDE, which is called the Korteweg-de Vries equation, which models movement of waves in shallow water, in channels. So I won't go into much details about the physics of the system. And well, the Korteweg-de Vries equation that we will look at is non-linear because of the term WWX, but we will in fact linearize the equation after. But it is also, it emits some disturbances, which are D1 and D2. And it has a control at the boundary. These disturbances are in fact constant in the sense that they don't depend on the time. And because D1 for sure depends on X, so it's not constant, but it's constant with respect to the time. Okay. And the question that we have is quite classical in automatic control. It is that given an output, which is here given by WXT0, the question is it possible to design an output feedback law, so a control which depends only on the output, such that this output goes to some given reference as t goes to infinity, where R is a given reference, and this despite the disturbances. So this is quite classical as the question, but solving it for PDE might be difficult. But to explain how we are going to do this for the Korteweg-de Vries equation, I will show, well, the steps design for the control design for a simple ODE, a really simple ODE, which is just given by this ODE. So this is a scalar ODE because W is just a scalar for all t. And you just have a control and a constant disturbance. Okay. So here the output is quite clear, just W. And you want to design a feedback law, so which depends on W, such that the limit when t goes to 0 of W minus R, where R is a given reference, goes to 0. And to achieve this goal, in fact, it is not possible to use a static feedback law. Okay. Why? Because if you take U is equal to minus KW, and even if you make depend U on R, then you cannot stabilize the systems such that W goes to R, because the equilibrium points will always depend on D. So you have to use instead a dynamical feedback law, and this dynamical feedback law is, in fact, a PI controller. So the PI controller is quite well known from the community, but I wanted to emphasize on this fact that I understood quite recently, in fact, and which is the following. So the integral action, in fact, adds a dynamics, and by adding the dynamics, in fact, you are changing the equilibrium points of the system. Because if you look at the equilibrium points of the system, then you end up with W infinity, which is equal to R. But the equilibrium point of Z is something which is not zero, but it doesn't matter because you just want W to go to converge to R as T goes to infinity. So this is the point of the integral action principle. The integral actions modifies the equilibrium points, and the proportional actions stabilizes W. So this is more or less the principle of the PI controller. And the question now is, okay, you modified the equilibrium points, but how we can select Kp and Ki so that you have the output W that goes to R as T goes to infinity. For sure, to treat this case, this is quite simple. If you look at the frequency domain approach, it is really simple. But here I want to explain how you can do it with a Lyapunov approach, and more precisely a forwarding approach, which is maybe not optimal in this case, but that will help understanding how I did it, or we did it, in fact, for the KdV equation. So we consider W bar such that it is equal to W minus W infinity, and Z bar such that it is equal to Z minus Z infinity. And so you just have to, in fact, stabilize these equations. So this is a cascade system, and you want to stabilize it. And the first step is quite simple. You want to pre-stabilize the equation by considering Ki Z bar as an input or a disturbance. And you want to design an ISS Lyapunov functional. Here, this is quite simple. It's just the energy of the system. And if you take Kp positive, then you can prove that the system W bar equal to Kp W bar plus V is ISS. So this is quite simple. Then, to stabilize the cascade system, you consider this Lyapunov functional, so which is composed by the first ISS Lyapunov functional that I have introduced before, and the second term, which is a term that we may call the forwarding term, because it is this kind of Lyapunov functional is related to the forwarding method that has been developed in the finite-dimensional setting, and more precisely for nonlinear finite-dimensional system. But here I just used this kind of method for a linear ODE, but it is maybe too strong a tool to treat this case. But still, what is the principle of the forwarding method? The idea is to look at this term, so the difference between Z bar and MW bar. And so the idea is to select a M, okay, this term M, such that you have Z bar which converge to MW bar. So first MW bar which converges to Z bar, but no, this is the contrary, sorry, Z bar that converges to MW bar. And you know that W bar already converges to 0 because of the first step, okay? And so this means that Z bar will converge to 0 because W bar also converges to 0. So this is the point of the forwarding method. Well, this is a point of view. So I know that Kokotovic, for instance, has another point of view, or even Jean-Michel Coron has another point of view about the method. Okay. So we pick M is equal to -1 over Kp, and by computing this term, the time derivative of this term, you end up with this equality. So you can see that you have Z bar square that appears in a negative way from a sign point of view. Okay? So now you have the Lyapunov functional, the time derivative of the Lyapunov functional, which is given by two terms. The first one that comes from the ISS Lyapunov functional that we have designed before, and the second terms that comes from the choice of M. And so you just have this first term, okay, W bar. And so you just have to apply the Young's inequality and you find some conditions on Ki and B such that you have the Lyapunov inequality that you want. So as a recap, this is a 3-steps design. You first find or build an ISS Lyapunov functional for a system. Then you use the forwarding method. And from this forwarding method, you select the gains. And in fact, this is exactly the same strategy for the KdV equation. Okay? So if you have any question, you can interrupt me, in fact, during the talk. So before considering the first steps of the case where you have you want to build an ISS Lyapunov functional, we want to know what is the stability properties of the KdV equation, because maybe you don't need any gain or any control so that you stabilize the equation. And in fact, this is the case here because the origin of the KdV equations is globally exponentially stable as soon as L doesn't belong to this critical length set, which is maybe horrible to read, but which comes in fact from the analysis, the spectrum analysis of the system. And to illustrate this problem, you just have to look at this example. So you know that the natural energy of the system, when you take the time derivative of it, you have this equality, okay? And if you pick L is equal to 2 pi and the initial conditions, which is equal to 1 minus cos x, then this term will be equal to 0 at t is equal to 0. So the output will be equal to 0 at t is equal to 0, which means that the energy is conserving. So this implies that you have the Lyapunov stability, but you don't have the attractivity of the origin. Okay. And there is also something which is important here, is that the output, in fact, is exactly observable if and only if L doesn't belong to the set that I have mentioned before. In fact, the result that we have seen before comes from the paper that I cited here from Rosier in 1907. Okay, and this is quite clear because from the example that we have seen before, if you pick L is equal to 2 pi and y0 is equal to 1 minus cos x, then the output may vanish. Okay, so since we want to do an output regulation of this system with the output wxt0, we have to have the exact observability. This is quite clear. So here, since we focus on the linear KdV equations, even if we have some result for the nonlinear KdV equations that comes from some fixed point theorem, but I won't go into much details about this. So since we focus on the linear KdV equation, so we will assume that L doesn't belong to N. Okay, so we don't have any problem here. So what does it mean? It means that the open loop is already exponentially stable. That implies that we don't need a proportional action because the system is already stable without perturbation. Okay, and so we just have to add some integral action. Okay, so to treat this kind of PDEs, there exist some results. So I just cite some of them. So results from the semigroup approach that has been found mainly by Lyapunov. And well, these kind of results are quite general, quite interesting, and they are based on the frequential approach, but it is maybe difficult to apply. And in fact, it is difficult to extend the results that have been found for this kind of system to nonlinear system. While the Lyapunov approach that has been extended, so that has been developed by Alexandre Terranjan, Vincent Andrieux, and myself, in fact, needs stronger assumptions to the existence of ISS Lyapunov functional, for instance, but it is a constructive approach, maybe, and also you can extend this result to to nonlinear systems. So this is the differences. I don't say that one approach is better than the other one, because I think that the semigroup approach is maybe more optimal than the Lyapunov approach in the linear case. So here are the main results that we have obtained for this system. Okay, so first it is a well-positiveness result, which is quite, that I won't discuss much more, that I won't discuss that much because, well, it is quite classical. And it says that as soon as you have initial condition in L2 times R, then you have a weak solution. And as soon as you have initial conditions in the domain, so the domain is given by this, this space, then you have strong solution, okay? Here you can see that you have some condition on K, so K has to belong to some interval 0K star, but you can weaken this assumption and just prove that for any K you have existence of solution, but it's just that the solution will only exist on a small interval of time, okay? So the proof is based on the semigroup approach, quite classical. You just prove that the operator is maximal monotone. So this is not, this is quite classical, so I won't discuss this theorem. And the second theorem that I will discuss more is the stabilization and regulation theorem that we have found. So this theorem just tells us that ZW will converge exponentially to the equilibrium points of the system, and it is also stable. Okay, so this is what says this inequality. And moreover, if you have the initial conditions that belongs to the domain, the space that we have introduced before, then the output will go to the reference as t goes to 0. So this means that if we are in the domain, then we are considering strong solution. And this is quite normal because here we are considering an output, okay, so a trace of the solution. And so we need the trace to be well-defined, and for the trace to be well-defined, we need to introduce strong solution, okay? So I will first define what I mean by the equilibrium points of the system. So the equilibrium points of the systems are given by this boundary value problem. Okay, so this is, so you can solve this equation. So this is not that easy, but you can solve it. But what I want to emphasize on is the last line of this boundary value problem, which tells you that the output at infinity is equal to R. So this is because we added some integral action in the system. So this is exactly as in the finite dimensional case. And we will after consider the change of variable, and so that you just, instead of considering the case where you have disturbances and references, you have just this equation. And something that I want also to say is that if you stabilize the equation, so the cascade system that I have presented before, then you regulate the output as soon as you consider strong solution. And to prove it, it is not that difficult. You just have to multiply the KDV equation by the W bar, then you integrate and you perform some integration by parts so that you end up with this equality, okay? Then you bound the output by these terms. And since you consider some the strong solutions, you know that W will converge to 0, but W bar T also will converge to 0. And you have also that Z bar converge to 0. So that means that W bar will converge to 0 as T goes to infinity, okay? And in fact, in the following, we will focus on the case where D1 is equal to D2 is equal to R is equal to 0. So we won't take care of the disturbances in the following. Okay. So I will recall again what is the general strategy. So first, as I told you, we want to build an ISS Lyapunov functional for the K-Levy equation. So a functional such that you have this inequality. And to do so, we will use two tools. So first, a strictification tool that I will explain. And second, an observer designed by the backstepping method. In fact, the strictification technique that I will mention, that I will explain, is based on the design of observer. And it comes from some results that has been developed for a finite-dimensional system. Then, as soon as you have this Lyapunov functional, this ISS Lyapunov functional, you use the forwarding method. And this forwarding method is based on this second term, which is quite the same than in the finite-dimensional case that I have introduced at the beginning. But M here is no longer a scalar, but rather a linear operator. And here we will use two tools, so the forwarding method that I have introduced before, and also the Sylvester equation, so that we can define M. Okay. So first we will talk about the strictification. So we have this K-Levy equation, okay, with a U, okay, that will be then equal to KZ, okay. But you just look at this U as a disturbance. This is not important, okay. And you know that when U is equal to 0, okay, you know that 0 is exponentially stable. But the proof, the classical proof that has been found by Lionel Rosier, for instance, is not based on the construction of a Lyapunov functional, but it is rather, it uses, in fact, the exact observability of the output, okay? And so from the proof that has been found before, it is maybe difficult to prove an ISS property. So maybe with some semi-group theory, you can do it, but to do it in a constructive way, this is maybe difficult to do it. So what we wanted to do is to prove it in a constructive way. And so let us recall that the time derivative of the energy along the solution gives this equality, okay? So we know that when U is equal to 0, the non-positivity of this term here is ensured, but the right-hand side depends only on the output. So what does it mean? It means that the energy function, so the energy here, is a weak Lyapunov functional. It is not a strict Lyapunov functional, because to have a strict Lyapunov functional, you need the right-hand side of this equality to depend on the full state, on the norm of WL2, okay, in a negative way. Okay, so what we want to do with this weak Lyapunov functional, we want to strictify this Lyapunov functional. So what is a strictification? This is quite simple from the word strictification. It consists in modifying a weak Lyapunov functional so that you make it strict. So there exists an extensive literature about this in the finite-dimensional setting. For instance, a book by Madisov and Mazank in 2009. But we have also some results due to Christophe Prieur and Frédéric Mazank in 2012 that has been developed for hyperbolic system, transport equations. But here we will use a different approach than the approach that I have mentioned here. We will strictify E with an observer. Okay, how we are going to do it? Well, we will first suppose that we have a converging observer, okay? So we have the converging observer, which is given here. We consider W tilde as the difference between W and W hat. And then you have this observer, and you suppose that for this system, okay, for this system, there exists an ISS Lyapunov functional that satisfies this inequality, okay? So you have this is quite nice, but now you come back to the KdV equation that we have seen before, and you add this term, so pxwxt0, and then you add also minus pxwxt0. So you end up with the KdV equation that we have seen before. You use the ISS Lyapunov functional that we have seen before, and it is almost the same thing than before. It's just that you have these terms in red that appears, and which appears in a positive way, from a sign point of view. Okay, so not good, but just remind that the energy, the time derivative of the energy, make appear in a negative way the output. Okay, so if you choose the Lyapunov function as a EW plus UW with a which is large enough, then you can kill the term that appears here. Okay, and so you have an ISS Lyapunov functional for this KdV equation. So the idea is quite simple, I think, and quite elegant. So I can tell it because it's not my idea at the beginning, but it was, I think, nice to apply it for the KdV equation. But the question now is, okay, we have supposed that we have this observer, but how we can design such an observer, and what is P here? Well, in fact, to design the observer, we will apply the backstepping principle. So maybe some of you knows already what is the backstepping method. So it is based on a linear transformation that maps a system into a target system, which has been chosen to be exponentially stable. Okay. So this is a quite well-known technique in the automatic control theory for PDEs. So it has been developed mostly by Miroslav Kuświcz and his co-authors. And so the challenge with the backstepping method is, okay, first we have to select a suitable gamma. So the gamma will be the state of the target system that you want to map this system to. Okay, so selecting a suitable gamma is not a big issue. This is quite simple. Then you have to prove that the transformation is boundedly invertible, because this means that if gamma is exponentially stable, then W also will be exponentially stable. Okay, so this is quite difficult in general, mostly because here you don't have a Volterra transformation, okay, but you have a Freedom transformation. And it is a Freedom transformation because the integral goes from 0 to L, in contrast with Volterra, where you have, for instance, the integral that goes from X to L or to 0 to X, depending on the PD that you are looking at. Okay? So in the Freedom paradigm, this is more difficult, I think. And then you select P. And so, okay, gamma, it is quite simple. You just choose gamma such that it satisfies the KdV equation, but with a damping. And thanks to this damping that acts in all the domain, then you can prove that the natural energy of this system satisfies the desired inequality. Okay, nice. And now, okay, you want to prove that this transformation is boundedly invertible. And to do so, you have to determine what PD satisfies the kernel P, okay? And this PD is quite difficult to analyze because of the term, the Dirac here, delta x minus y, and because also of the term PYYY, PXXX. So this is really difficult to analyze. But thanks to Coron and Liu, we didn't have to analyze this equation because they proved in another context than this one, that there exists a unique solution to this equation, and that the transformation here is bundlely invertible. Okay? And here you can also deduce P from the kernel, and P will depend on the kernel. Okay? Okay, as I told you before, as soon as you have the proof that pi is the transformation is bundlely invertible, you can bound W by gamma. Okay, but you know that gamma for the gamma is ISS, and then you can prove that the W is ISS also. Okay, so you have a Lyapunov functional, ISS Lyapunov functional for the system that you want to study, the first system, not the target system. Okay, so we have two Lyapunov functionals. The first one is for the observer, okay, which is P minus 1W, and the ISS Lyapunov functional, which is given by this term. And so for the KdV equation, we have an ISS Lyapunov functional. We have built it with a strictification technique. And I find it interesting because in contrast with most of the results in backstepping, so maybe there are some other results which did this. In contrast with most of the results, here we have used the backstepping method to build a Lyapunov functional, not to stabilize a system, because the system was already stable. Okay. And so now we go back to the system we want to stabilize, which is a cascade system. Okay. As I told you before, the Lyapunov functional we want to use is a Lyapunov functional which is based on the ISS Lyapunov function that we have built before, and the second terms which we may define as the forwarding term, which is the difference between Z and MW. Okay. So what is M in fact? So M solves a Sylvester equation, which is given by this equation. But well, I called it a Sylvester equation. Maybe it's not fair because here A is equal to 0, but these Sylvester equations can be also useful in other cases for the output regulation, more precisely when the disturbances you want to reject or the references you want to converge to are depending on the time. Okay. But still, this is the Sylvester equation, a really simple one. And invoking the result of Fong, you know that there exists a unique solution to this equation. So maybe it's not useful to invoke this result because you know that S is the operator which is related to the KdV equation without coupling. Okay. And you know that without coupling, so with Z is equal to 0, this KdV equation is already exponentially stable. So this means that S is invertible. Okay, that's nice, but does there exist an explicit form for M? So first, you know that the operator M can be explicitly written like this. This is a theorem of representation that is due to Vries, because this is quite well known. So you can see that in the forwarding case, so in this case at least, this is again an integral transformation, okay? But here the kernel is quite more easier, so it is easier to deal with because it doesn't depend on another term, so on y, for instance, on another variable. So you use the Sylvester equation to note that here you have this equation, okay? And then you do some integration by parts, and you end up with M that solves this boundary value problem, okay? So this is a boundary value problem, and in contrast with the backstepping method, it is not a PD. And this boundary value problem is quite easier to solve. In fact, you have even a unique explicit solution, which is given by this term, this function. Okay. So now we do some computation, okay? You take the time derivative of this term, z minus mw. You use the Sylvester equation here, okay? And you end up with this term, so minus kz squared, so this is nice. And here you have a cross term. And then, using the ISS property of the ISS Lyapunov functional that we have built, you have this term, okay? This term. And then using Young's inequality, you can kill, in a sense, the cross term that we have seen here. And so you can prove that there exists C such that you have this inequality, and you, using this Young's inequality, you also obtain a condition on K such that you have the stabilization of this cascade system. Okay, so I didn't mention this in the abstract that I sent, but I wanted also to if time allows, and I think that time allows me, I wanted to show that this ISS Lyapunov functional can be also used in other situations than the output regulation. And I want to show that this ISS Lyapunov functional can be applied also in the case of the singular perturbation. So what is the singular perturbation, and when do you want to apply the singular perturbation? It is, in fact, a case where you have systems with different time scales, okay? So this appears in many situations. So for instance, if you have a mechanical system coupled with an electrical system, then the electrical system will be way faster than the mechanical system. And for this kind of system, this is quite difficult because, for instance, in numerical simulation, you have to adapt the numerical scheme with respect to the differences between the two time scales. So this is quite difficult. And even in stability, that might be difficult. And what does the singular perturbation? It tells, in fact, that, okay, the fast system, in fact, can be neglected. And the singular perturbation tells you that, okay, it can be neglected, and we have a proof that it can be neglected as soon as the fast system is sufficiently fast. So I will explain it after. So here is the system that we want to look at, okay? So this is a KdV equations coupled with the ODE. Sorry. So this is quite similar to the system that we have seen before, just that it is more general in the sense that here before B was equal to 0. So here it is more or less a situation where you have a system where the actuator has the dynamics. You can see it like this. In contrast with the system that we have seen before, where you imposed the dynamics. Here, the dynamics is imposed. So question for this system is, okay, what are the conditions on A, B, C such that the coupled system is stable? And do these conditions change when epsilon is small? So this is what I said before. If epsilon is sufficiently small, which means that the KdV equation is sufficiently fast, do we have conditions that are easier to deal with? So for this system, and for any epsilon, we know that with the same Lyapunov functional than for the PI controller that we have seen before, we know that there exist some positive values, A star K1 and K2, such that A is sufficiently small and AC minus B is between K1 and K2 that are positive, such that the origin of this system is globally exponentially stable. So as I told you, this result can be seen as a generalization of the latter results, where B is equal to 0 and C is equal to 1. And okay, so this is nice, but what about the case of small epsilon? And in this case, we use some specific tools from singular perturbation techniques. So what is the singular perturbation techniques principle? So the principle is to decoupling the coupled system into two approximated systems that will describe the differences between the dynamics. So the first one is the reduced order system, which will describe the slower system. And the second one is the boundary layer system that will describe the faster system. The question is how we can compute these two systems. Well, in fact, you just have to take epsilon equal to 0, okay? So taking epsilon equal to 0, you end up with this boundary value problem, okay, that you can solve. In fact, it is quite similar to the system that we have seen before, the Sylvester equation that we have seen before. And so the explicit solution to this equation is given by this equation. You know that Wxt0 in this case is equal to minus AZ. And so if you replace this term in the dynamics of Z, you end up with this reduced order system, okay? And if B minus AC is negative, then this system is exponentially stable, okay? And you can see that, so we have seen before that AC minus B was between two positive values, which means that B minus AC is negative. So this is a condition that already appeared before for all epsilon, okay? For the boundary layer system, you change the time scale, so you consider tau, which is equal to T over epsilon. We do some computations that I won't show here, and we use the fact that epsilon is equal to 0, and then we obtain the boundary layer system, so which is a simple KdV equation, and you know that if L doesn't belong to N, then the system is exponentially stable, okay? And what tells our result, it tells that as soon as ABC is such that B minus AC is negative, then we know that there exists an epsilon star such that for any epsilon belonging to this interval, the origin is globally exponentially stable, okay? So this is quite nice. And what tells this result? It tells that, okay, if epsilon is sufficiently small, then looking at the stability of the coupled system reduces to looking at the stability of the two subsystems, okay? But, well, this result is true, in fact, in the finite-dimensional setting. So it is true because if two finite-dimensional systems that are coupled are, so the two subsystems are stable, then for a sufficiently small epsilon, you will have that the full system will be exponentially stable. But this is no longer the case for some examples in the infinite dimensional case. And you can find examples in these papers by Tang Mazanti and Serpa and Priya. And just to have the sketch of the proof, the idea is to change the coordinates. So here you have W minus the 2fxaz. So fxaz is the solution of this boundary value problem, okay? It is given here. And so doing this computation, you end up with this coupled system. And you can see that, okay, if epsilon is small or equal to 0, then you have a KdV equation which is stable, okay? And here you have the ODE, which is stable with the output of the KdV equation, which is for the KdV equation is already stable. So you can, so by intuition, you can deduce that the system will be exponentially stable as soon as epsilon is sufficiently small. But to prove this, we used the same Lyapunov function done in the PI case, and by considering this term here as a perturbation, okay? So to conclude, so what we have done here, we have built an ISS Lyapunov function for the KdV equation, which is, I think, quite nice. And we have applied it for different different applications. So for the output regulation, and for the case where you have KdV equations coupled with a slow ODE. We also did it for the fast ODE coupled with a slow KdV equation. And we have some open problems for the KdV equation. So for instance, what about the nonlinear case? Okay, so for the KdV equation, so you can do it with the fixed point theorem, at least for the stabilization, but it can be also interesting to look at the full system, so the full nonlinear system, especially in the case where L belongs to N, because in this case, the KdV equation without the coupling, so just the KdV equations, you know that the system is exponentially, no, it is polynomially stable locally. And to do so, we can follow some results due to Jean-Michel Coron and Yvonne Rivas, and also Shengquan Jiang, that has proposed a control that is time varying. What could be also interesting in the output regulation technique, in the output regulation task, is to consider the case where you have disturbances that are time varying. And in this case, the Sylvester equation that we are looking at is maybe more difficult. And so we may, for instance, follow some results due to Daniele, Astolfi, and Laurent Praly, and many other authors, in fact. And something that could be really interesting and that could mix the two results that I have presented is we may also use singular perturbation techniques for regulation purposes, as in a recent result due to Lorenzetti and Weiss. So for sure, it is not the only result that mixes the two techniques, but it might be really interesting to use these techniques for this case. And that's it. And thank you for your attention.